Earlier class we have solved Schrodinger equation in two-dimensional Cartesian coordinates. First one for the free particle and second one for a particle subjected to a two-dimensional infinite potential. Well, in this lecture we shall do the similar calculation, but in this case in the polar coordinates or theta coordinates. The time in the Laplacian, the operator Laplacian in r theta coordinates reads as 1 by r del r of r del r plus del theta 1 by r del theta. So this is 1 by r del r of r del r plus 1 upon r square del 2 del theta 2. This is the Laplacian. So the time independent Schrodinger, if we consider a free particle in polar coordinate, that is a Cartesian coordinate system, we have assumed x and y. The particle points is denoted by either xy or in r theta. This part has been worked out earlier, and here the particle is free particle. That means it can move any direction, in any direction, and the particle doesn't have any dependence on theta. So we first write the time independent Schrodinger equation. This is minus h line square by twice m, and then this part 1 by r del r on r del r plus 1 by r square del 2 del theta 2 operating on psi of r theta, and this is e of psi of r theta. According to separation of variable technique, we use the wave function as r of r and big theta of theta, where capital R is a function of r only and big theta is a function of theta only. When we plug this in into this equation, we get capital R by capital theta, this part, this is ddr of r dr. Since small capital R are function of small r only, we are not using the partial derivatives, but we are not using del, but we are using d. Note this change. And then from this term it is r by r square d2 theta d theta 2, and this part, if we multiply this, it is minus twice m e by h line square, which one likes to write this way. Now we then r theta, so this is minus k square r of theta. Now for non-trivial solution, we divide both the sides by r theta, so that this equation becomes 1 by small r capital R ddr of r dr plus making too much of mistakes. Now you see that this term has r dependence. To avoid the r dependence, we multiply both the sides with r square. So multiply r square both the sides and rearrange the term. So this is small r by r ddr of r dr. This term is plus k square r square. We take it on the other side, minus 1 by theta d2 theta d theta 2. So left hand side is a function of r only, and the right hand side is a function of theta only. They are always equal. So we write it as the separation constant alpha. Now the theta equation becomes this gives you a solution which depends on alpha as e to the power plus minus I alpha theta. It is by convention it is written as e to the power alpha theta, where alpha can take positive and negative values. But one thing remember, that capital theta at theta is equal to capital theta as theta plus 2 pi, which leaves that alpha must be integer, and it is generally denoted by m, so that m can have values 0, plus minus 1, plus minus 2, as we have seen in vector array model. So it is written as m square, where m is integer. And another thing, there are all possible values of m, since for a free particle it can move in this direction and it can move in any direction, and there will be no directional aspect. So the solution must be independent of theta. So for circular symmetry, all the allowed values of m is 0. Due to circular symmetry, the solution must be independent of theta, which implies the m is 0 in this case. So we derive this differential equation, the R equation. The R equation is this. This becomes, you multiply R with this, and on simplification this becomes R squared d2R d2 plus R dr dr plus k square r square minus m square r is equal to 0. Remember that it is the Bessel function of order m. It is Bessel equation. So the solution is, let me come to right here. So we see that this high solution is m dependent, and it is some constant which is 1 upon root 2 pi. From normalization, that psi m star this gives you 2 pi. Particle, and the R equation becomes r square d2r dr2 plus r dr plus k square r square plus minus m square r is equal to 0. So this is the Bessel differential equation, and the solution is can be written as, in general, the r depends on m and k, so it depends on m, and kr is equal to am jm of kr plus bm y. This is the Bessel function of first kind, and this is the Bessel function of second kind, or the Neumann function. Note that this function has divergence at the origin, have divergence at r is equal to 0. Now remember the graphs of y, so they goes to negative infinity. On the other hand, the j graphs of j, this is y or n, and this is jm. For 1 0 it has such types of variation. This is j0, variation of j0, and all other j starts from j1 j2, all are 0 at the origin. Only j0 is equal to 1 at the origin. Now the wave function that we have obtained has to be finite at the origin. So the boundary condition is that Rm has to be finite, Rm has to be finite at the origin. This defines that Bm's are 0. So the solution is AmJm. But we know that m is equal to 0, so the solution is R0 is equal to some constant times j0 of kr. So the total solution of the wave function is, it depends only on k and nothing else, and r theta, basically it is a function of k of r, and we modify it another constant a j0 kr. The wave function j0 asymptotic, if we note that the Bessel function behaves like this. This period, if we consider the period, this period is slightly less than pi, and as we go away to higher values of r, this period tends to pi, tends to 2 pi, but its behavior is damped sinusoidal. That is, Jn for x tends to infinity behaves as sin x plus b cos x by root x. You recall the asymptotic behavior of Jnx. So it gives you a damped sinusoidal with an asymptotic region. And there is no restriction on the k values that can be taken up, and since there is no restriction on the k values, the energy is continuous. Now I come to we come to the solution that a particle confined within a two-dimensional cylindrical wave, well, that is, we consider this is the x coordinate, it is y coordinate, we consider a well of radius a such that v is 0 here and v tends to infinity. So the bound In this case, we see that the particle wave function will be non-zero within the well, and this must be zero at psi has to be zero outside as well as on the rim of the well. Now if we carry out the procedure as we have done in the earlier case, we see that within the well, that is within the well, that is well means r less than a, the phi wave function, the theta dependent wave function is Im theta, where m is equal to 0, plus minus 1, plus minus 2, and so on and so forth. And our equation depends on two things. One is on m, another one is on k, and for the wave function to be finite at the origin, it must be am jm of kr, where jm is the this is the Bessel function of first kind of order m. Now come to the normalization. In the case of rectangular well, we haven't talked much about the normalization, just quoted the normalized wave function, but here we shall consider the normalized wave function. So for a particular m, the wave function depends on m and k, and it is r theta is equal to this is the wave function. Now the normalization condition is that psi m now the integration is over r dr d theta. R ranges from 0 to a and theta ranges from 0 to 2 pi is equal to over circle of, or disk, we shall call it disk of radius, circular disk of radius. It is the integration is over this, so this part will be, we consider first the am modulus square upon 2 pi, this obtained from when we square this, then the e to the power minus Im theta e to the power Im theta d theta integrated from 0 to 2 pi. Minus Im theta coming from the starred quantity, and here we will have Jm as it is real, where Jm star of Kr r dr integrated from 0 to a. One thing is that this will lead 2 pi, so it is am square, and then we will have Jm square Kr r dr 0 to a. Recall the normalization property of Bessel function. The normalization condition of Bessel function is x j nu square of x, in terms of we call it x j nu square of alpha x dx from 0 to a. This is half a square j nu plus 1 of alpha a, and this is am square a square by 2 j m plus 1 ka. These values are available. Sorry, there is I think there is no square in it. So this is the square. This is the normalization constant, and if we know that this is one condition, normalization aspect. Now we come to the boundary condition. This should be discussed earlier, I have forgotten. The boundary condition is that the wave function psi of a theta has to be 0 for all theta, that is the radial wave function Rm of k, Rm of, sorry, it is kr, Rm of kr, Rm of ka has to be 0, and this is equal to am jm of ka is equal to 0. Here we consider the zeros of special Bessel function, and that indicates that jm of ka is equal to 0 is equal to this indicates that ka must be equal to chi of ms. These are known as the zeros of jm of order s. Let us consider J0 and explain what is this. The graph of J0 is like this. So this first index name goes to J0. So this is the first zero of Bessel function. So this is x01. This is x02, x03. If we consider the Bessel function of order 1, the graph is like this. So this is x of 1 1, this is x of 1 2, this is x of 1 3. So these are known as the Bessel function, and they are available in literature. So we see that the k values are no more continuous. There are only few k values which are given by the zeros of the Bessel function. That is to say that k is quantized. We write k is equivalent to k depends on m and s, and it is given by x s by a. So this is the quantization k values. Since k is quantized, e goes as h line square k square upon 2m. E is quantized. So you can calculate to find the values of E. E depends on M and as well as on S. So we see that if we consider a free particle in polar coordinate, the energy values are continuous, the energy spectrum is continuous, and when we confine the particle within a ring of radius A, the energy values becomes quantized. The wave and these are the allowed momentas moment, as I am speaking it momenta, because if we multiply by each cross we will get the momentum values and the corresponding quantized energy values. Now we come to the last example of this case, the harmonic oscillator, 2D harmonic oscillator. Here we have finished the 4 cases that I have promised. A free particle in xy and r theta coordinate system, an infinite potential well in xy and r theta coordinate system. In now our is 2D harmonic oscillator. This, if we consider this is x coordinate and y coordinate, then we consider a particle. This particle is acted upon by this Fy is equal to minus ky y, and it is acted upon in x direction by a force f of x is equal to minus kx x. It is ky y. Such situation arises when the atoms are stacked on a plane. We consider atomic size. They are within a plane, and each atom is interacting within its neighbors. If we assume the small amplitude oscillation, then we can replace the interaction by as if they are connected by springs. These are the springs in one direction. Let me denote the atomic size by red colors. These are the atomic size. These are the spring. The blue colored are the springs along y direction, and we denote the springs along x direction by green color. So if we consider any particle, it is being under the action of two restoring force, one along x direction and other one in the y direction, and this resembles the harmonic oscillator in 2D. So for this, the potential energy is a function of this. It is half kx x square plus half ky y square. In terms of omega, you can write half omega x square plus omega y square, where omega x square is equal to kx by m and omega y square is equal to ky by m. If we write the Schrodinger equation, time dependent Schrodinger equation for this case, the time dependent Schrodinger equation is h line square upon twice m, h line square upon twice m, del 2 del x2 plus del 2 del y2 psi of xy plus v of xy. So v of xy, for v of xy we write We can easily decouple it into two equations. One is minus h line square by twice. We first introduce the separation as per separation of variable technique. We use the wave function x of x and y of y, and then the x equation becomes minus h line square by twice m d2x dx2 plus half m omega x square is equal to exx, and this one is minus h line square by twice m d2y dy2 plus half m omega y square y is equal to ey capital Y, where we have written E is equal to total energy as the sum of energy along x motion and sum of energies along x and y motion. This can be converted into the wave function that x of x depends on a number, and we consider u as the dimensionless variable, so that this is nx factorial to the power minus half h nx of u e to the power minus u square by 2, where u is equal to m omega x by h line, and the corresponding energy along x direction is h line omega x nx plus half. And for this motion we write y of it depends on v, again similar expression, this where v is m omega y by h cross, and ny is ny so the total wave function now depends on two quantum numbers in x and y. It is uv whole thing to the power minus of e to the power minus u square plus v square by 2 h nx u h ny v, and the corresponding energy is nx plus half for symmetric oscillator. For symmetric oscillator, special case arises for when omega x is equal to omega y, that is k is equal to ky. If omega x is equal to omega y is equal to omega, then E becomes This is h cross omega nx ny plus 1, and the question of degeneracy arises. Now consider the ground state. The ground state is E00, corresponding the wave state is psi 00, non-degenerate. First excited states is having the energy for first excited state E is equal to E01 or E10. So the energy is 2h cross omega, and this corresponds to two sets psi 10 and psi 01, so twofold degenerate state. This symmetric oscillator can also be solved in r theta coordinate system, and I am not going to that discussion here. By this we finish our discussion on Schrodinger equation in 2D. In the next class we shall go to the Schrodinger equation in 3D, but 3D